Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello, welcome back. I hope you're well. In the last episode, we talked about enthalpy and enthalpy changes, and we mentioned it's much easier to measure an enthalpy change during a reaction than it is to try and determine the absolute energy of something. And so in this episode, we're going to be talking about measuring energy changes and standard enthalpies. So let's start by talking about standard enthalpy changes. These are definitions of an enthalpy change during a particular process to a mole of substance or to create a mole of substance. And they always relate to the reaction being done in standard conditions. And those standard conditions are pressure of 100,000 kilopascals and a temperature of 298 Kelvin. Now those are chosen because 298 Kelvin or 25 Celsius is considered to be room temperature and 100 kilopascals is considered to be the metric atmospheric pressure. So when we talk about standard enthalpy change for a particular process, we're always talking about the amount of energy change under those conditions. And these are really worth learning because not only does the syllabus love to use definitions, but in my experience, examiners love to test that you've learned those definitions and that you understand them too. So do learn these. We're going to talk about two in particular, but there are a lot more. So look at your syllabus and see what there is and make sure you learn them, make sure you're ready for them when they come up in assignments, when they come up in exams. The first one we're going to talk about is the standard enthalpy of formation. And this refers to the enthalpy change when 1 mole of a substance is formed from its constituent elements, those elements and the final substance being in their standard states. What do we mean by their standard states? It means that if one of the substances, the elements or the product, is in a particular state, gas, liquid or solid, at 100 kilopascals and 298 Kelvin, then this enthalpy change is considering that that reaction was done with those substances in that state. So if one of our substances was water in one of these enthalpy changes, water is in the liquid state at 298 Kelvin and 100 kilopascals, and therefore the reaction will always refer to water being used or created in the standard state. So the standard enthalpy of formation of a substance is the enthalpy change that happens when 1 mole of the substance is formed from its constituent elements. The other standard enthalpy that we need to be aware of, that we really need to focus on, is the standard enthalpy of combustion. And this, as the name suggests, is the enthalpy change that occurs when 1 mole of substance is completely combusted in sufficient oxygen. For example, the enthalpy change that occurs when 1 mole of ethanol is completely combusted with oxygen. And these and other standard enthalpies are known values that would often be given on an exam paper that exist in data booklets. They are standard values. If you're expected to use them in an examination question, you're going to be given those values. Okay, so that's great for theoretical values for doing calculations. How about if we need to make an enthalpy change measurement in the lab? How can we do this? Well, there's various ways to do this, and it depends exactly what the reaction process is as to which way would be the best way to measure the enthalpy change. To measure the enthalpy of combustion, usually we use a simple flame calorimeter. And this would consist of something like a spirit burner with the substance that we're going to burn. There would be a vessel, perhaps a beaker of water above that burner, perhaps on a tripod, so that the heat energy given out by the combustion goes into the water in the beaker. We would have a thermometer and a stirrer, measure the temperature of the water prior to starting, and the temperature change that occurs during the combustion. And it's important to know exactly how much water is present in that beaker, exactly what mass is present. It's also important to know exactly how much of the substance, the ethanol, for example, that is in the spirit burner before we start and after we finish the combustion. So we would weigh that before and after to find out how much of the ethanol is burnt. So to do this experiment, once we're set up, ignite the burner, stir the water, measure the temperature change over a period. And once a sufficient period has passed in order for it to be a viable measurement, we can put out the flame on the spirit burner, stop combusting the ethanol, make a note of the temperature change that's occurred. Once the spirit burner's cooled, we need to make a note of the change in mass of ethanol that was present. Then we use a simple equation, Q equals mc delta T, to work out the energy change that's happened. Q is the amount of energy, M is the mass of the water, C is the specific heat capacity of the water, and delta T is the temperature change of that mass of water. Be aware that the value Q, the amount of energy, is going to be in joules, and although we'll get a positive result if we're combusting something, the enthalpy change is going to be negative. So once we've calculated Q, the number of joules of energy, we need to convert that into kilojoules, and then we need to refer it back to the mass of the substance burnt. We need to know how many moles of substance was burnt so that we can calculate what the energy change per mole would be. And when we've got that, don't forget to express your exothermic result, as this will always be, as a negative value. Even though Q came out as a positive value, Q is just the amount of energy released. The enthalpy is going to be negative because that was an exothermic change. Okay, so that's great for things we can combust. How about if we're doing a different sort of reaction? If we're doing, for example, a neutralization. Well, in this case, we can start by having our two reactants in aqueous solution separately in known volumes of water, and then we can mix them together, often in a polystyrene cup or similar, so that we limit the energy loss. We would stir with a thermometer as that's happening. We'd know the temperatures before we started. We measure the maximum temperature change that occurs, because that is going to indicate when the reaction is complete. And then we'd use that same equation, Q equals mc delta T. Q being the number of joules of energy change that happens during the reaction, M being the total mass of the water when both reactants were brought together, it's the total amount. C is still the specific heat capacity of the water, and delta T refers to the temperature change that occurred in that mass of water. Once we've calculated that Q value, the number of joules, again, we need to convert that to kilojoules. We need to understand how many moles of substance reacted, or if it's a neutralization, how many moles of water were produced, because enthalpy of neutralization refers to the number of moles of water produced. And then we can work out the number of kilojoules per mole. So that will be the enthalpy change per mole for the substance that we're considering. Again, be aware of whether this was an exothermic or an endothermic change, and make sure we express the enthalpy change as negative if there was a rise in temperature because it was exothermic. If it was endothermic, as some reactions can be, express the enthalpy change as a positive value because the temperature decreased during the reaction. Finally, one of the questions you'll be asked quite a bit when you're writing up your lab or explaining within an exam question is, why might that value not be the same as the expected value? Why might it not be accurate? So consider the limitations of those experiments. In each case, there are places where temperature might be lost, although we might have used a polystyrene cup, and we may have tried to limit the effects of any movement of air. There will be energy loss to the surrounding air. There'll be also energy absorbed by things other than the water. So, for example, in our flame calorimeter, some of that energy change will have gone into the beaker, some of it will have gone into the gauze, etc. Looking at how frequently and how effectively the stirring of that water happened. Is that temperature change an accurate measurement or not? These are just a few of the things that might affect the accuracy of the measurement of the amount of energy that changed during the reaction that happened either in the lab or that is described in an exam question. Okay, so that brings us to the end of this episode. We've talked about standard enthalpy changes and the fact that they refer to 1 mole of substance under particular temperature and pressure conditions, standard conditions. We've talked about how we might actually do an experiment to measure an energy change using a flame calorimeter, or by conducting a reaction within, for example, a polystyrene beaker and monitoring the temperature change. And we've talked about how to do the calculation and refer it back to the number of moles of substance. We talked about whether that should be negative or positive, depending on whether we had a temperature rise or a temperature decrease. And we also covered a few of the possible reasons why the actual measurement done in the lab might not be as accurate as we would expect. We might not get the exact measurement that is the official measurement that we might see in a data sheet or a data booklet. Okay, if you've any questions on this topic, please do get in touch. And the best place to do that is over at our podcast Patreon community. That's patreon.com/chemistry made simple. That's where I'll be answering the questions that you bring up, so please do so. I really look forward to hearing those questions because I know this is quite an in-depth topic and I really want to help you on this. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistry made simple, where you'll be able to ask deeper questions about this topic and get more support for your studies too. So I look forward to speaking to you again in the next episode, and until then, do look after yourself and goodbye.